What if you could turn the most common stuff on Earth, water, into a giant radio antenna? An antenna that could listen for one of the planet's most invisible and serious dangers. It sounds like something out of a sci-fi movie, right? Well, new research suggests it might actually be possible.
So how do you find a danger you can't see, hear, or feel? This is the fundamental problem with nuclear radiation. To map out a danger zone, you have to get close. But getting close is the one thing you absolutely can't do. It's this classic catch-22 that scientists have been stuck with for decades.
All right, so to really get why this new idea is such a big deal, we've got to talk about the problem first. And that problem, well, it all boils down to the tricky nature of something called gamma rays.
Okay, here's a great way to think about it. Gamma rays are like sprinters. They're packed with incredible energy, but they burn out fast and get blocked by almost anything. You have to be right at the finish line to even know they were there. Radio waves, on the other hand, they're the marathon runners. They can go on for miles and miles. And that difference, that is the key to this whole thing.
And this is where things get really cool. A team of researchers from Amrita Vishwavidyapitham in India came up with this radical new idea. They looked at this old problem and asked a question that is just so clever, turning to a corner of physics that not many people had really looked at before.
So scientists have known for a long time that when you blast water with radiation, stuff happens. Molecules break apart, it gives off a little bit of visible light. But what these researchers noticed was huge. Almost nobody had ever seriously looked into whether water might also be giving off radio waves. And that little gap in the research, that was their starting point.
And that leads us to the absolute core of their work. I mean, just think about it for a second. What if you can use any body of water, a lake, a river, maybe even just the moisture in the air, and use it like a natural converter, a device that takes those hard-to-find short-range gamma rays and transforms them into long-range radio waves that are super easy to pick up from a safe distance. It's a genius concept.
Okay, so how does this actually work? I mean, how on earth does water take a gamma photon and spit out a radio signal? Well, it turns out it's this fascinating microscopic chain reaction.
It all kicks off with this incredibly violent atomic-level collision. So you see that incoming wavy line? That's our gamma photon. And it just slams into a water molecule. The impact is so powerful that it literally knocks an electron right off, sending it flying. And that one little event, that's the trigger for everything that comes next.
So that first collision is just the start of this cascade, like a set of atomic dominoes. The electron that got knocked loose goes on a rampage, smashing into other water molecules and breaking them apart. And in all this chaos, you create these special hydrogen atoms that are just buzzing with way too much energy. The fancy name for them is Rydberg atoms. And, like a kid who's had way too much sugar, they have to release that extra energy somehow. And how do they do it? They broadcast it out as a very, very specific radio signal.
Right, and that specific signal, it has a name. Radio recombination lines, or RRLs. And thinking of it as a radio fingerprint is perfect. Every time one of these super excited hydrogen atoms chills out and drops down to a lower energy state, it sends out a little ping on a very precise radio frequency. So if you know which frequency to listen to, you can hear them. So here's the really crucial takeaway. The gamma radiation is effectively turning the water into this huge army of tiny, microscopic radio transmitters. And the best part? They're all broadcasting on the exact same channel. Even a single gamma photon can create hundreds of these little broadcasters. It's pretty amazing. Okay, so this all sounds fantastic in theory, right? But here's the million-dollar question. Is this signal actually strong enough to detect, or is it just a whisper in a hurricane? To figure that out, the researchers had to run some seriously complex computer simulations.
And what did the simulations show? Well, the actual strength of this radio signal from a single event is, honestly, mind-bogglingly small.
Get ready for this number, 10 to the minus 21 watts. To put that in perspective, that's a decimal point followed by 20 zeros and then a 1. I mean, it's an impossibly faint signal. But, and this is the absolute key, a real radiation source isn't releasing just one photon, it's unleashing trillions upon trillions of them. And this is where the numbers really start to work in our favor. Even though the signal from one photon is tiny, each one is surprisingly productive. Check out this chart. A single gamma photon creates about 330 hydrogen atoms. Now, out of those, around 120 of them are the exact kind we need, the Rydberg atoms that broadcast in the L-band, a frequency that our detectors are great at picking up. So, one photon creates over 100 tiny radio transmitters. All of a sudden, that faint whisper gets a lot louder. Now this right here might be the most critical finding in the whole paper. The researchers found a direct predictable link. Up to a certain point, the more radiation you have, the stronger the radio signal gets. For any kind of detector, that's the absolute jackpot. But they also found a limit. At really high doses, the signal just stops getting stronger and eventually kind of drowns itself out in noise.
So why does it top out like that? Well, it's due to a physics phenomenon called Stark broadening. Basically, when the radiation gets extremely high, you're creating so many charged particles in the water that they all get too crowded. They literally start getting in each other's way.
The best analogy is just what it says here. It's like you're trying to listen to your favorite song on the radio, but there's so much static on the line that you can't make out the music anymore. It all just gets blurred and drowned out. At those extreme radiation levels, all our tiny atomic transmitters are creating so much interference for each other that their clear signal turns into a bunch of indecipherable noise.
So, okay, even with that limit at super high doses, this discovery still opens up a completely new way of thinking about monitoring radiation. Let's dig into what this could actually mean for the future.
Seriously, the potential applications here are wild. Just imagine. There's a nuclear accident. Instead of sending people in close, you set up a simple radio detector miles away and measure the radiation by listening to a nearby river. Or you could fly a drone over a huge area and map contamination in a few hours, not weeks. You're essentially turning the environment itself into a giant connected detection network.
And this brings us to one last, kind of mind-blowing thought. Our planet is almost 3/4 water, right? So could this discovery one day let us turn our oceans into a single, massive, passive radiation detector, a global alarm system constantly listening for the faint radio whispers of invisible danger? It's an absolutely incredible possibility to think about.